Hello, I'm Chris Kennedy, Space Architect. Today's lecture on space engineering is about surface-based design and considerations and exploration habitat design and considerations. So just as a reminder, when we're thinking about design definition analysis, we need to consider the inputs, in other words, from the customer and the stakeholders, and understanding the needs and objectives and concept of operations and put that into the system analysis and control. So we go through the requirements analysis, the functional analysis, and synthesize the design through trade studies, design considerations, etc. So when thinking about designing surface bases or exploration habitats, think about the destinations and the environments by which you're designing them for, whether it be for low Earth orbit, remote destination here on Earth, like the ocean or Antarctica, the lunar missions, either lunar orbit or lunar surface, deep exploration missions, interplanetary transportation, or Mars missions, be it the surface or the moons of Mars. Also consider, as a reminder, the spaceflight, human spaceflight operations, crew operations from the internal of the spacecraft or habitation, the external operations, crew operations, such as EVA activities, the mission operations, the science operations, and also don't forget the logistics and maintenance, which are important aspect to consider. This is a reminder of human exploration systems. You have a number of elements that have to work together to enable and meet all the mission objectives. Elements such as the crew return vehicle, a deep space habitat, exploration vehicles or surface rovers, EVA capabilities, propulsion if it's an interplanetary transportation, power generation storage, thermal rejection systems or radiators, deep space communications, docking systems, robotic systems, logistics and spares, resupply and storage, maintenance and repair. Just a reminder, there are a number of ways to get in and out of habitats, and airlocks and nodes are those transition spaces or vestibules, as we use them here on Earth, to transition from an internal space, a habitat, to the external space, be it the space environment. And so when looking at that, there's these components, these elements, airlocks and nodes, become that transition space between the habitat and the exterior. So let's talk about surface-based definition. There's a good reference book, The Human Spaceflight Mission Analysis and Design by Wiley Larson. I worked with a couple of co-authors on chapter 13, Design, Sizing, and Integrating a Surface Base. We also developed a chapter for design, sizing, and integrating a habitat, but the book decided to break that up into different subchapters and integrate those among the book. So the chapter on designing habitats, actually we turned into a white paper and a conference paper. So as far as for designing a surface base, first you need to be determining the mission objectives and understanding and defining those needs, goals, and objectives, the functions, the requirements, the concept of operations, and also identify the constraints and assumptions and available resources. Next step is developing the surface base. Outline a development scenario, a mission, a design reference mission, and define required capabilities for that surface-based elements. Part of that is understanding and selecting the site and laying out the base. So selecting a site using selection criteria is very important. Identify your options, rank your candidates, and select your site based on the mission objectives. Then you get into sizing and integrating the base zones and elements. Develop conceptual design of each of the elements and develop an integration plan and schedule. And think about the development, your end state of the base. So you want to think about the end state, how you want it to finally be at the end of its development, but also think about the initial development phases. when you first land, the site preparation, as you grow and mature from one habitat element or module, and maybe several after that, or inflatables, or even using ISRU to build your habitat and structures later on. Once you have that in hand, you can then begin to assess the costs and the risk of the layout of the base, and then document and iterate. So this design process is iterative, like layers of the onion. You keep peeling it back, and you keep doing more and refining, and redoing the design to better meet the requirements and objectives. So it's all part of that research, analysis, and design. When talking about surface exploration, you might want to think about it in terms of phases. So you have your surface exploration sorties, which are robotic and or human sorties. Apollo was an example of surface sortie with humans. Then you get into base planning, and you may start out with a surface research outpost, a minimal capability, research capability for humans, or being human tended, that they can go there and perform research and exploration. That may mature into an initial outpost with more capabilities, more modules, more support functionality. The next step or part of the phase really is about resource production utilization, becoming Earth independent. So your initial concept may only have plunked down a module or two for initial research, but as you mature, you want to bring in mining equipment and so on to be able to process the soil and make use of the volatiles and minerals that is there on the moon for making new products and products that can be used. At this point, you've now matured into a surface base, a mature surface base with multiple capabilities and functionalities. Once you've really kind of established that and become Earth independent, now you're in that industrialization phase where you can produce products and services for additional people or different capabilities on the moon or in low Earth orbit or low lunar orbit. And then, eventually you're going to be a sustained human presence. Much like we've attained that on space station, where we have sustained human presence, we've been living there for 20 plus years. So when you're thinking about surface outposts or base considerations, consider your mission objectives and your science objectives. There will always be science and mission objectives. And so you want to understand those, because those drive the needs and understanding of capabilities to meet that objectives. Again, doing the site location and topology, understanding that. So that's a good consideration in that environment. Look at your sun angles, look at where you might be able to locate solar arrays, look at where you might be able to locate your launch and landing capabilities and so on. Understand also where your ISRU resources are, that you want to be kind of close proximity to that, so you don't have long traverses of the delivery of those resources once they're produced. And then you also need to look at your ascent and descent trajectories. The landing and launch area location, think about your blast ejecta and surface preparation, unloading large payloads and transporting them to the outpost. Typically, if you're in the equatorial region, your descent trajectory is right to left or west or east to west. So you're coming across the lunar orbit and descending onto the lunar surface. You also will need, obviously, to establish a communication system, ground antennas, and relay systems perhaps as well. Power generation, so you've got options on power generation, solar dynamics, solar power, or even nuclear options. Also consider dust control as one of those considerations. It can be a very big deterrent and be very difficult and hard on mechanisms and systems. So anything you can do to put down roads or paths or mitigate the dust is a good thing. And also then, like we were talking earlier, Think of a master plan. Your initial stages of development, as you mature through various stages of development, and what's the end state? What does your end final outpost or master or the base look like? Here are some environmental factor considerations that influence surface-based design. Partial gravity, it affects the design of equipment and fluid mechanisms. You have the vacuum and the low atmospheric pressure, which is critical connections, seals internal pressure of the habitat and EVA suits. The thermal environment, controlling the temperatures, protect all surface elements. Moon energy storage for lunar night is very important because you have the day-night cycle on the moon, which is different than here on Earth. 14 days of daylight and 14 days of night. However, at night there is earth shine and you can see somewhat, but you certainly do not have the capability to collect solar power if you're in that region. Now, if you're on the South Pole at one of the high points, topography wise, you possibly can have sunlight all the time, and which is great for solar power systems. Again, the surface lighting, keep in mind that there is earth shine, but you will need some artificial lighting, especially in those areas where it's dark or shadowed. The dust environment, the moon has very abrasive ground glass, so protect your mechanisms, remove from the EVA suits, try not to bring those suits into the habitat because those fine particles of dust or ground glass will then become airborne and get into your lungs. Also, radiation is a big item to protect the humans from, and not just the humans, but the equipment as well. And so you want your sensitive equipment protected or rad hardened. You can protect from solar rays with using a storm shelter, but the galactic cosmic rays tend to just go through everything unless you have a lot of protection. And many of the scenarios or options include burying or creating bulk regolith over your habitats, or creating shelters out of lunar concrete or 3D printed shelters, and then placing habitats within that so you have the protection. On the moon, you will have to protect from micrometeoroids and blast ejecta, similar as well on the Mars, but not quite as much because of the gravity and some atmosphere. And then surface resources. Think about the availability of those resources, produce the propellants and consumables, and 3D manufacturing raw stock materials. So that could influence your location of your base. And surface topography and features. Obviously, some areas are very blocky with ejecta from meteors hitting the moon and creating craters. And so those craters could be hard to get down into. Also, lava tubes, great features to want to be able to set up habitats in, but difficult to access and get into. Other aspects to consider are the space environmental considerations. Here is a chart that goes over the considerations, vacuum, debris, gravity, radiation, and dust, and then different aspects, whether you're in Earth orbit, lunar Mars interplanetary transfer, or lunar Mars surface. And I'll let you look at those at your leisure, but certainly there are different aspects to take into consideration. Debris in low Earth orbit, you have orbital debris, which is a big problem, and quite large particles. Micrometeoroids are still an issue, but they can be handled a little bit differently. And so you don't have orbital debris in the Mars interplanetary transfer or Mars surface, obviously, or Mars orbit. Not yet, anyways. So mission factors to consider and what their influences are on surface bases. You have the mission objectives and the science objectives. Those typically are your required capabilities for science, SRU, habitation, laboratories, etc. You have the destination, which sets the environment, as well as the time to duration to get there. the number of crew, which is a required total pressure volume, and crew free volume, the psychological well-being, the mission duration, the total time, and that influences the total amount of pressure volume that you need, as well as redundancies, spares, consumables, life support items, etc. And then the launch vehicles, the logistics, infrastructure, and transfer vehicles. All of these have influences, are factors on the design. The launch vehicles are the constraint on the size and mass that it can be launched to low Earth orbit or translunar injection. The mission risks, the safety of the crew, the safety of the mission, fail safe and system reliability are important aspects of consideration. And surface-based evolution, design for growth and expansion. When applicable, you're again looking at your mission objectives. And then the mission costs. Examples are technology, using off-the-shelf technology versus advanced technology, in which case you will have to do some DD&T to develop that. There are numerous surface elements that are utilized in surface habitats. And for habitation, you typically have, for short duration missions, you tend to use the pressurized rovers. For long duration, you want more of a permanent habitat or habitation capability. Laboratories and surface-based science, again, for very short duration, for up to a couple weeks, you may want to use pressurized rovers. Longer than that, you may want to consider a laboratory module. EVA activities in airlocks, you have to consider the type of suit, whether it's hard, soft, or hybrid, and then whether you have an airlock, a suit lock, and the dust control, spares, and suit maintenance, etc. Power generation, you may have internal power systems for very short duration with batteries and some solar arrays, and long duration, you definitely want surface development. So you may have a power generation capability. It could be solar arrays, solar dynamic, a combination of them. Actually, you need also the battery systems, energy storage for the lunar night. And another option is nuclear. And so for thermal control, for short duration, you could consider integral power systems for integral thermal systems, body mounted radiators, or you could have long duration surface deployment and stuff. Life support, again, for short duration, you may want more of an open system, and then you want to get a degree of closure or full closure for long duration as much as you can. Communication, navigation, you need to think about line of sight, satellites, and versus direct comm, and the time delays and lag in communications for like Mars. Surface transportation and construction equipment and emplacement equipment, you need to consider and look at unpressurized and pressurized transport systems, unload and transport of large payloads, base infrastructures, site preparation, mining, construction equipment, etc. Robotic, many robotic systems in that. For in situ resource utilization, you have to think about both mining and bulk storage, transport and manufacturing capabilities, and then the resource storage. You also need to consider the logistics and resupply. For short duration missions, you may take all your consumables and logistics and resupply and spares, but for long duration, you think about how to resupply, how often, how much, and how much you're going to keep at the destination for spares, etc. This is a notional outpost master planning and layout. You can see there's 5 zones. There's science zone, power zone, industrial zone, launch and landing zone, and the habitation zone. There's interconnectivity, interdependency between the zones. In some cases, the science zone, you want to leave pristine and you want that away from the habitat or the surface base area. Power, depending on what it is, could be placed in proximity to the habitation zone, but if it's nuclear, you want to get it a little further away and protected. and buried if necessary. The industrial zone, certainly that's going to be a dusty mining operation zone. And so you'd want that, separate that away from your power zone if that's photovoltaic. And then launch and landing, obviously you would want to place that also away, but in proximity to your industrial zone so you can take advantage of those consumables that are produced, or the propellants produced from the ISRU process. But you also want the launch and landing zone at either north or south of the habitation zone if you're flying east to west, which is typically the trajectory from the subject matter experts at NASA that I've talked to. And so you do not want to be flying over the habitation zone or taking off over the habitation zone. So you'd want the launch and landing either north or south of the habitation zone. This was an example of a surface base that I designed back in '92. You have your habitation complex or habitation zone. The science zone was off to the west. The launch and landing was to the south. So your landing vehicles were coming from the east, heading west and landing. The ISRU was off to the east, and then the power production was off to the north. So you can see some of the guidance there to keep your systems separated, but also you do not want to fly over certain areas. Okay, let's talk now about space habitation design and considerations. So what is space habitation? Basically, it's the recreation of Earth's environment for the purpose of sustaining human life, a place for humans to live and work in. So habitats are those pressurized crew volumes for the purpose of living and working in space. So they include multiple functions like living, food preparation and dining, recreation and relaxing, sleeping and privacy, crew health care and exercise, working in laboratories and research areas, mission planning and conferencing, transition spaces, as we talked before, such as nodes or airlocks, utilities and subsystem spaces and functionality, logistics, maintenance, and repair. In thinking about space habitats, we have defined them as three classifications, three categories. Class 1 is a pre-integrated habitat module. It's Earth manufactured, Earth assembled, and fully outfitted, pre-integrated and tested prior to launch, space delivered with immediate habitation capability once you're connected to the rest of the system. It is launch shroud constrained and is limited to launch vehicle payload size and mass capabilities. Class 2 is thought of as a prefabricated deployable space or surface deployed and assembled. So it too is Earth manufactured, but it requires space deployment, assembly, and outfitting. It requires robotic and human labor during assembly. Its partial integration capabilities for the subsystems requires some of the internal outfitting and emplacement. Critical subsystems on Earth are tested prior to launch. It requires assembly and checkout prior to human occupancy. It can deliver large volumes, large capable volumes. It's not necessarily restricted to the launch vehicle shroud, although the packaged unit would be, of course. And it is restricted to launch mass and could be delivered on multiple vehicles. An example is an inflatable like the Transhab design. The Class 3 is the in situ derived and constructed habitat. This is something that would be make use of the space resources, lunar or Mars, and then ISRU in space constructed. Requires robotic manufacturing capability, and infrastructure requires robotic and human labor during construction. It requires integration of subsystems, and it requires internal outfitting and placement. Then the critical subsystems probably are Earth-based and tested prior to launch, but still requires assembly and integration one at the destination. Very large volumes are possible, and it is not restricted to the launch vehicle size nor the launch mass. Um, so if you look at this graph, you can see, currently we're here and we're building integrated hard shell modules, aluminum lithium cans, or some composites. And Space Station is a prime example of that. This is an integrated surface habitat design that we did during the Constellation program. And the technology level is pretty straightforward. And so as we move forward in evolution in time, we're now starting to see that prefabricated deployables, inflatables are being more and more looked at and utilized and thought about. And then the ISRE derived are really becoming well known now, and beginning a lot of people looking at this as a way to really build our infrastructure, to build our facilities and capabilities and habitats on the Moon and Mars. So I feel space architecture is kind of at a tipping point, and this will be the tipping point by which where we really start to move towards in situ derived structures, or these class 3 habitats. The space architecture industry will really take off and be more utilized when we start thinking about these types of design and structures, and the architecture of the future will be driven by these kinds of structures. These are the elements of a space habitation system. The subsystems are made up of the structure or enclosure, and there's a description of each of these. So obviously the structure or enclosure is the basic structure or enclosed to contain the pressure vessel, if you will. Then you have environmental control and life support systems. Obviously that's to keep the humans alive. We need to breathe oxygen. We need to get the CO2 out of the atmosphere. We need to have temperature regulation. We need to have waste management, storage, water, etc. Thermal control is important. Active thermal, there is passive and active thermal control. The active thermal control is about collecting the heat within the habitat and dissipating that heat external of the habitat. Obviously, there's power generation, power management, and distribution internal to the habitat. Data management, the data management system and communications. There's internal audio and video, very important for crew communications and crew situational awareness. There's the crew accommodations, experiment or research equipment, storage, and supplies and consumables, and a radiation shelter or a storm shelter for solar proton events. So here's some of the things to think about in the design approach. Each habitat requires a different design approach. You have to consider your mission objectives, your science objectives, the overall location, in other words, the destination and environment, but all have to meet the requirements of providing the pressurized environment for humans to live and work within. So common requirements, regardless of destination, include the following: acceptable physiological and psychological support for the humans. Those characteristics, the design, the internal layout, very important, the human-centered design approach. Successful accommodation of the mission and science objectives, reliable structural integrity with adequate safety margins, forgiving failure modes, in other words, leak before rupture, ability to be tested at a high level of confidence before being put into service, the ability to be integrated with available launch systems, straightforward outfitting and servicing, easily maintained and serviced, long design life, and commonality at the system and subsystem level. So commonality between the power system cards, the specific design control cards that go into the power system could be also used in other aspects of the card change out. So if you have, think of it as your motherboard or your cards in your computer, and how you can update them or pull them out and and create new capability or functionality within your computer system. So that's important to think about that commonality throughout, such as pumps and filters and so on. So here is a recap of the space habitat design steps. Assess and determine the design application. Is it orbital, transfer, planetary surface? Assess the environmental constraints, the location, gravity, debris, vacuum, radiation, dust, etc. Assess the human considerations. Define the function, the physiological and psychological well-being. Define the habitat system elements, external system elements and internal subsystems and interfaces. Determine those key design decisions and trade studies, environmental, human, subsystem, etc., and determine and define the design criteria and determine and define the evaluation criteria. So you could, for design criteria, you would have programmatic, human system integration, engineering, operations, training, manufacturing, and assembly. Here are some kind of key design decisions and key trades. So we have the design driver on the left, the human like habitat function, the effect of that, and then the kind of a rule of thumb. So for habitat function, you can have either a habitat layout as a habitat only, or a habitat and a laboratory, or a laboratory only. This rule of thumb is to separate hab and laboratory functions and activities, separate work from living spaces. The number of crew and affects the volume required. Long duration, you want to have over 50 cubic meters of total pressurized volume per crew member, and that's total pressurized volume. That is not the net habitable volume. Mission duration, the affects the habitat size, short, medium, and long durations. The structure, the aluminum, lithium, composites, or inflatables. Inflatables are good for delivering large volumes for long missions. The hard shells are good for small volumes, short missions. Life support, you have to consider open, partial, or closed, and the percent of openness. Data handling and management, consider the computers and automation and the autonomy or mission objectives. Communications, you may have direct or relay. You got to consider the person to person, person to spacecraft, spacecraft to ground. Thermal control, you could have body mounted radiators or a separate structure. Power generation, you could have solar arrays, body mounted solar arrays, depending on the size of the system, or you could have a independent large solar field or nuclear and so on. And what you want to consider there is the kilograms per watt being produced. For crew accommodations, the physiological and psychological aspects of free volume, private and social spaces, and the separation of those spaces. For environmental protection, you've got to consider the effects of radiation and dust. And then for risk, the level of redundancy, fail op or fail safe on critical items. So when thinking about space habitation design options generation, these are the kind of questions or issues you'll be faced with. So when you think about the design approach or aspect, the habitat size and volume, what is the required volume? Will it be able to package in the launch vehicle? If not, what are the alternatives? The habitat mass, account for all external and internal subsystems and interfaces, do a bottoms up assessment of all the masses. The life support system, what is the required or desired level of self-sufficiency, if any? The technology readiness, are those items ready to be brought online? The degree of integration, is the habitat fully integrated or does it require some level of preparation or assembly and integration? Power supply approach, options could include batteries, fuel cells, solar arrays, solar dynamic, and nuclear. Communications approach, options could include direct or indirect relays or through satellites. Thermal control, again, you've got options which include passive and active systems. Crew accommodations, so the crew accommodations tends to look at things as tolerable, which is austere, performance-based or performance level, or optimal for comfort. And then the risk approach, again, thinking about the level of safety and redundancy. fail-op, fail-safe for Crit 1 systems. Options include protection from radiation, orbital debris, micrometeoroid, and dust, and healthcare should be included. So when talking about exploration of habitat subsystems, these are the typical subsystems that you would be including: structures and mechanisms, environmental protection, life support, power management distribution, avionics, C&DH, communications and tracking, thermal control systems, crew and medical systems and bays, laboratory, science and research areas, logistics, repair and manufacturing area support areas, EVA, and robotics. So this is, I think I went through this already, but this is the subsystems and their description of each subsystem. And obviously the structures and mechanism, the structure is a basic structure and enclosure to contain pressure. The mechanisms are things and items such as docking systems, hatches, grapple fixtures, etc. I'm not going to read through all these. You can look at the descriptions of each of the subsystems at your leisure. There are human factors and effects on partial gravity to consider: walking and running, posture, jumping, and handling equipment. The differences between the Earth gravity and then habitat design impacts. A couple of things to note is, especially in partial gravity, is to consider traction surfaces, consider the types of footwear you're wearing and the traction surface to help you, enable you to start walking or running in that gravity environment. So when we talk about functions or functionality, these are the types of functions that should be included in exploration habitats. You can see there's a structures discipline, mechanisms, power, thermal, ECLSS, fire safety, crew systems, avionics, comm, GNC, imagery, EVA, science, and robotics. And then there's functional titles. So there's sub-functions within that structures discipline, from the system volume, human rated pressure volume, habitable volume, stowage volume, internal and external loads, micrometeoroid. So the internal loads could be secondary structure, internal module viewing through hatches, translation aids, grapple fixtures, robotic accommodations, structural health monitoring. So when you're doing and thinking about the functions of a habitat, this will give you a good idea of the functions that you need to be thinking about incorporating into your habitat. So look at each one of these disciplines, look at each one of these functions when it comes time for you to begin thinking, what functions, functionality, and subsystems do I need in my habitat? So this is actually a good checklist for you to look at. Here's some additional functions having to do with more of water or ECLSS closure, waste or water and waste reclamation, and so on. The ECLSS air and monitoring and control and things of that nature. You also need to consider the external subsystem interfaces of a habitat. And the habitat has several aspects to consider. The habitat system itself has the an interface for element to element or element to surface, or both. The structure mechanisms, you need to think about the station, the vehicle, the surface structure, docking mechanisms, etc. Mounting mechanisms if you have solar arrays and communications antennas, and so on. Life support, ECLSS, you could have external water and oxygen tanks, fluid, so you'll have fluid transfer and air transfer pass-throughs through the habitat, either through a bulkhead or a port. So each one of these external subsystems, there's going to be an interface through the habitat. And so you need to consider and take that into account, those interfaces, and make sure that is accounted for. This shows a diagram, a rough diagram of those interfaces, both internal and external interfaces for a habitat. Here's some rule of thumbs for habitat sizing, and can be useful to get you started, because a lot of times, unless you do the detailed analysis, do you really know how much volume is required for all your equipment and crew volume, etc. So from a habitat, laboratory, and airlock, This will give you a rough idea of some first order magnitude design parameters. So from a standpoint of total pressurized volume per crew member, now this is not the net habitable volume. This is total pressurized volume, which would include the equipment and the extra spaces and so on. So for short duration, under 30 days, it's roughly 10 cubic meters per crew member. For medium or duration missions, which is 30 to 180 days, it's 20 to 50. And that varies a little bit. If you're trying to do a minimalistic approach, it'll be less. And then long duration missions are considered over 180 days, and we target about 50 cubic meters. So if you had 4 crew members, this would put you roughly about 200 cubic meters, which is about right for a long duration mission of 4 crew members. The mass, you can follow that across and see that gives you rough ideas. And so this work, these numbers, rule of thumb, come from numerous trade studies we've done over the years, and then we took all that data and looked at it and took our averages to understand how this was developing and how we understood that the results of all of our design work over the years. So this puts you in the ballpark. If you're trying to figure out how much power, depending on whether you're short, medium, or long duration, it gives you a rough idea of how much power might be needed per crew member. So this puts you in the ballpark if you have a separate or a laboratory, or if you're combining habitat and laboratory, and then an airlock element as well. So this gives you the basics of an understanding to get you in the ballpark for rough order magnitude sizing. So also part of our studies, what we did is we took and tried to do analysis to understand the mass fraction and volume fractions of this system for a habitat. And here it breaks down by mass and volume and by the subsystem. So this gives you a rough idea of how much, so if you're trying to get a rough idea, so in the previous chart, you get a rough idea of the total mass, and then you could take this number and be able to say, okay, typically in all the designs that have been done, you can kind of estimate that 12 to 15% is going to go towards ECLSS, so on and so forth, and then you could begin to do that breakdown. Obviously, the better way to do it is your bottoms up detailed design analysis, but when you're early on in conceptual design, you're trying to get your rough ideas of masses and systems and volumes, this will put you in the ballpark. An important aspect about any habitat is the design and evaluation criteria. So design criteria and its process, the design process is a method in which designers define the forms, function, and performance of their concept that address the need and constraints provided by the product's design criteria or their guidelines. Evaluation criteria is the internal habitat architectural evaluation, is an activity in which the design's forms, functions, and performance are evaluated based on expectations and objectives defined by the teams. So one is used as criteria to influence the design, to guide you in the design, to make sure you're covering different aspects about the design. The other is the evaluation of the design. So it's really important to define what criteria you're using in your evaluation and those definitions. So this is, so principles and standards influence what is defined as the design criteria, and that influences and directs in the design process by which you iterate and then you have your final design. These designs and during the process are evaluated, and the design criteria informs and builds the evaluation criteria, which standards and expectations and objectives are part of that understanding. You perform the evaluation process, and then you have an evaluation of the internal architecture, in which case you refine it, or redesign it, or you move on and baseline it. This is the habitat design criteria that we came up with a large cross-section of disciplines from a number of NASA centers. So we addressed it, and we went through all these criterias, and then we grouped them into buckets, and we grouped them into sub-buckets. So we have, these are all defined in a white paper, and it is on my on the site. So you have programmatic design criteria, which includes constraints, longevity, and strategic or strategy. And you can see the sub categories of like strategy is mission objectives, political alignments, and stakeholder agreements. Human system integration is a very large design criteria, obviously, when it comes to the habitat. So you're looking at behavioral health aspects, which are many important aspects to consider here. The ergonomics of the system and design, and then the internal habitat itself, organization of the hardware and crew systems, crew activities, interactability, variations of use, and so on. Operations and training is broken into interactions between crew and spacecraft, in situ education, ground crew, and on-orbit crew activities. Engineering is important because that has your design margins, your levels of testing, the system design influences, and sustainability. And you can read through all the subcategories, and their definitions, again, are defined. And then important part of this also is manufacturing and assembly. From the standpoint of Earth or element manufacturing, ground processing, and on-orbit internal integration. So each one of those are important design criteria to be considered when you're designing a habitat. And so let's talk about habitat evaluations. So you come up with, let's say, 5 design concepts, and you have a bunch of concepts. The first step is to do what we call a tabletop evaluation. And as an example, FY03 crew restraint evaluation. So you're vetted the evaluation precedents, and you evaluate these, you come up with your evaluation criteria, and you evaluate the design concepts. And one thing you also want to make sure is the concepts themselves are at all the same level of design definition. From that, you would select 1 or 2 of those concepts for further design development and definition. And then you may build a mock-up of that or a virtual reality model, in which case then you can do a walkthrough, a physical or virtual walkthrough, and evaluate the habitat. In which case then you down select, you may choose some of both, or you may just choose one of the habitat designs, in which case you come up with a final design. At that point, you then begin your habitat evaluations by building higher fidelity models and mock-ups, in which case then you can begin to do habitable volume assessments, user analysis, et cetera, and better a day in the life of the astronaut or that concept of operations in that environment, in that habitat, to evaluate it. Park task simulators are higher fidelity yet. They're operational, they work, they're functional, and they're performing, and they work. And so you can then test that. Like the Habitat Demonstration Unit was a park task simulation in which we actually had operating functional equipment within the habitat and could do that design, do those evaluations. Full simulation may be even a higher fidelity yet, in which case the crew would live inside the habitat for X number of days or weeks and do the evaluation in a submersive environment. So you are actually living and working and operating inside the habitat for several weeks at a time. Oops. So in evaluation criteria, you want to think about your figures of merit. Evaluation criteria is based and influenced by the design criteria. So you want to understand it from that standpoint. And evaluation criteria is tailored based on the types of evaluation, whether it's a tabletop, a walkthrough, a simulation, or day in the life, and the level of the concept maturity. So you would take these design criteria, and then turn them into evaluation criteria, looking at certain aspects of each of these to understand the evaluation criteria, your figures of merit by which you're evaluating. Master equipment lists are used in designing and doing the knowledge capture of your mass and volume of all your systems and subsystems and components. And this is a master equipment list breakdown by domain name. You have structures, power, thermal control, propulsion, if necessary, avionics and flight software, communications and tracking, guidance, navigation, and control, if necessary, life support, EVA, crew health and human performance, exploration science, and logistics. So thank you for your participation and attention. And if you can reach me anytime at chris@technoarchitects.com or chrisjkennedy@gmail.com. Thank you.